happy to introduce Brent Webster and Nick Mathis to talk about a project that we have with our orthopedic therapy assistant program that was brought to me from Mary Kay Arvin, who's in the audience here. They're building and designing an elbow joint simulation model for the occupational therapy range of motion assessment. All right, guys, I'll hand it off to you.
As he said, I'm Nick Mathis, and this is Brent Webster. And our apparatus we created is for the OTA department for range of motion assessment. You may ask yourself why range of motion is important. As you walk into the room, you used multiple joints out of your body, your knees, hips, and everything else. And if you consider not having the ability to use those, your life would be much harder. If you, say, couldn't pick up your cup of coffee, how would you handle that? In the occupational therapy assistant program, OTA students are taught how to measure this range of motion, which is the full range through which a joint can move. Say the elbow, for example, is extended and then can flex through its range of motion. As you see here, a student is testing Brent's shoulder range of motion, and he's using a goniometer, which is it looks like a mix between a protractor and a ruler. It's lined up with different joint landmarks to show that minimum and maximum range of motion. OTA students and practitioners use that range of motion diagnostic as well as provide therapy to patients and report to occupational therapists. Currently, the OTA department has quite a few large classes, and they don't have a standardized apparatus by which to train these measurement skills. And so instead of using an apparatus, students test one another to measure that joint range of motion. And one of the downfalls of that is that students help each other out. They'll whisper the answer or provide other sorts of assistance to the student being tested. And that doesn't necessarily reflect a solid baseline of accuracy for those students. Accuracy is important for range of motion assessment. It drives different therapeutic interventions such as stretching, muscle building, or even up to surgery. If you look up here, this is a X-ray of a patient with heterotophic ossification. That's bone growth outside of the ordinary area. And using range of motion testing could help identify this limitation. This bony mass would prevent a patient from rotating their elbow, or if it were somewhere else, another joint through its full range of motion. Each joint has a specific tolerance through which it can, for how accurate the measurement has to be. The elbow, for example, is a 5-degree tolerance. Some of the larger joints go up to, say, around 10 degrees per joint, and then smaller joints, such as the fingers, are down to single degrees for their capabilities. The objective of our project is to create an elbow apparatus for students to test and train on. It would provide consistency in training and competency in the overall assessment of range of motion testing. Little overview, we're going to give you a short anatomy lesson, talk about the requests and design process of this apparatus, the overall production cost, and final design choice. Based on Dr. Arvin's requirements, the apparatus has to mimic the same size and weight of a human arm, has to have the same anatomical landmarks as the bones, go through the full range of motion, which is 0 to about 150 degrees for the average person. Males go from 0 to 150, which is 0 would be counted where the forearm and the humerus are collinear, and then as it's flexed up to its maximum range, that's ordinarily around 150. Some people can go past that 150, and then many women and some males can go past that 0-degree mark to hyperextension, which goes for about -10 degrees. The joint itself has to be posable, have a digital feedback system, be easy to use. The entire system has to be portable, and the overall budget is $1,000 or less. The humerus, radius, and ulna are the bones we're working with. They make up the arm. And then the lateral epicondyle, if you feel the outside of your elbow, right here, that's a bony protrusion, and that's used as a reference point for occupational therapy assistants to measure that range of motion. The goniometer they use is lined up with its fulcrum and axis. The fulcrum of the goniometer is lined up with that lateral epicondyle. There's a stationary arm that lines up along the humerus, pointing towards the shoulder, and then the movable arm goes from the lateral epicondyle and lines up with the far end of the arm. And this is a set of images showing that assessment. Here you can see my arm has started to flex from the 0 degree mark, and the student has the goniometer lined up with that lateral epicondyle, and then through the entire range of flexion, I measured the maximum extension all the way up to the maximum flexion of that joint. The question is, how do we get to creating a apparatus? We need to mimic the humerus, radius and ulna, the rotation mechanism, and measurement device for the elbow area, and then it has to be interfaced with a structure to rest on a cart for affordability.
All right, our project can be categorized into 3 subcategories, the first of which is structure, second, measurement, and third, transportation. We set up a decision matrix to show all the requirements that need to be met in order for this project to be completed. This will be seen throughout the presentation to further understand that the requirements were met. First category is structure. Within this, we have the bones, rotation method, and the mounting system. In the selection of the bones, our first decision was to use dowel rods. Issues with dowel rods is they're not going to have the bony landmarks that are needed in order to do the measurements. Second option was to go with the simulator arm, which is extremely expensive, anywhere from $500 to $1,000, and they do actually lack the anatomical landmarks themselves as well. They're usually used for nursing students to put IVs in. They don't really have the bony landmarks. And then the third option was to use artificial bones, and these bones are actually cast from human bones, so they are anatomically correct and similar in size and weight. So here's the decision matrix that shows that the artificial bone is the selection we made. Next, we have the rotation options. For the rotation options, first we went with the servo motor. Servo motor is basically just a small device that's controlled by a computer with a program that allows it to rotate. This method would require the use of a computer, so as far as portability, you would have to have a computer and a power source at all times, which would limit the mobility of it. Second is a clamp option. The clamp option is inexpensive, but it would require 2 students to work together, one to move the bones to the position needed, and then the other to clamp the bones in that position. And then third is a ratchet and pawl method, which I'll explain here. Ratchet and pawl is basically a gear with angled teeth. The pawl itself engages with those angled teeth to allow it to only rotate in one direction. As it slips over the teeth, the pawl locks into place and doesn't allow the ratchet to move in the reverse direction. Some examples of this would be zip ties, turnstiles, and socket wrenches. And with our selection, we chose to go with the 72 tooth 48 pitch ratchet, which is about 1.5 inches in diameter and allows for 5 degrees of motion through each tooth. So for the rotation devices, the ratchet and pawl method made the most sense, so that's what we decided to go with. Next, we've got the mounting options. The first is a carriage bolt, which is a simple, inexpensive option that would allow the upper part of the humerus to be attached to a wooden tabletop mount, as you can see back here in the actual design. It would limit the mobility at the shoulder, so once set in place. You could not rotate the shoulder to better fit the student to read the goniometer. And then the second option is the swivel mount, which would allow the shoulder joint to actually move in a similar fashion as it does. You can move it in all different directions. It allows for the arm to be swung out and calculations to be made easier. So we decided to go with the swivel mount in this category. And then third, we have the measurement options. We went back to the servo option here because we could use the servo in the computer program to actually calculate the rotations through and figure out the angle through the computer itself. And the second option was the analog goniometer, which is the exact same thing as what the students in the OTA department use to measure the angle itself. This would limit the immediate feedback requirement, as you would actually have to go to the other side, check the lines, and make sure. So this does give you the human error. Students might read it wrong. And then last, we have the digital goniometer, which is just like the analog goniometer, except for it eliminates the lines and markings on it, and it actually reads the angle as it's moved. It continually gives feedback, so the student would just have to look at the angle that it's at, and that would be the angle that they need to record. So for this, the servo motor was actually already thrown out earlier because it is expensive and it would require a computer interface at all times. So we decided to go with the digital goniometer because it is the simplest to use, inexpensive, and it does allow for immediate feedback.
There's also the matter of transporting the device. Requests included a cart for transportation as well as storage for additional testing materials. The cart system or the transportation system has to be mobile, be lightweight, have some amount of storage, be stable, and adjustable as well. The two options we investigated were a mobile TV stand and a multimedia cart. One nice thing about the mobile TV mount is that this area here is adjustable, which would be nice for various student heights. If the student were very tall or very short, it could be adjusted to make it more accessible. The multimedia cart has a better storage option. It has shelves and is lightweight. It's pretty standard in most departments. And one of the driving decisions behind our final decision was that the multimedia cart was available in the OTA department. So it's got a low price of $0, and that's pretty nice as far as our budget goes. Has better storage, is easier to use, and it's more portable. So that was our decision on the transportation. And as Brent explained about the tabletop mount, it allows it's fitted to the car that was available. And the final design of the apparatus hangs over the edge for easy access. And there's a weight shown here that helps with the stability of it. It's also removable for tabletop use if needed. To recap our different options, the structure meets all the required options for all the requirements except for immediate feedback and portability, which are not necessarily relevant in that aspect. Similarly, the measurement device meets all of its criteria, as well as the transportation option. Combining all of those, we meet all the requirements that were set out in the beginning.
So for our materials and methods, first we went ahead and took dowel rods to use as a prototype before cutting into actual bones to figure out how to place the ratchet and pawl. So in the picture on the left here, you can see the placement of the ratchet and pawl. It was important to make sure that the center point of the ratchet and the center point of the pawl were just over an inch apart. That way the pawl would engage with the ratchet cleanly and it wouldn't slip through the motion. So in the picture on the right, you can see a pulled apart view of the actual dowel rod model. And the washers in there are actually used to keep space between the pawl and the dowel rods because the friction between the two didn't allow for smooth motion. And then the spring in the bottom there is actually hooked into the dowel rod itself and is used to keep the pawl engaged with the ratchet at all times. And when you want to extend the arm back down, you just pop the spring out and the arm is allowed to move back to its fully extended position. This is the final product of the left, you can see the digital goniometer attached to the inner portion of the dowel rod model. The digital goniometer's center point acts through the center point of the dowel rod itself so that it can stay at the same arc as the arm so the angle is measured accurately. And then the picture on the right is just the model put together with the ratchet and pawl and the spring engaged so that the pawl is actually engaged with the ratchet teeth. In the final design, it took a little more work. We actually decided that we needed to keep the ratchet from rotating within the bone so that the pawl could engage and allow for full motion. In the picture on the far left, you can see the steel plate there actually acts as a spring. It keeps the pawl engaged with the ratchet at all times. And the copper wire is actually ran through a hole that is drilled at the top of the pawl. You pull that back and it allows the pawl to disengage from the ratchet and allows the arm to return to its fully extended range. And within the humerus there, I'll explain later how the ratchet's placed in there. In the middle picture, you can see the digital goniometer attached to the inner portion of the arm, and it is reading about 90 degrees there. The far right is the final product, which we have sitting up here. So this is a detailed picture of the humerus itself. On the far left, you see the front view of the humerus, and you can see the slot in the middle that was actually cut using a bandsaw, and it's just over 1/8 of an inch thick, and that is because the ratchet itself, the face width of it is 1/8 of an inch. We needed to allow a little room so that it could move, which we ended up changing anyways. It's actually glued to the ulna so that it cannot move. It rotates within the humerus, but it doesn't rotate freely. It rotates along with the ulna. In the middle picture, at the very bottom, you can see the hole that's drilled through the side of the humerus that allows a bolt to run through the ratchet to keep it in that position so that it stays there. That hole was actually there when the bones were purchased, and we tested it to make sure that it did act through the center. The hole above is for the pawl mount. This hole is actually hidden on the final product, but this hole took a lot of geometry and work to figure out where to place it so that the pawl could be dug into the humerus and engage at all times. The hole just above this is where the all-thread rod runs through to keep the digital goniometer attached, and it is set at that depth. And on the right-hand picture, you cannot see the digital goniometer hole because we don't want it to be visible from the student's side. So there is no rod running through the side outside of the arm.
We also have a look here, buddy, for Dr. Davis. This is highlighting where the lateral epicondyle is. If you've had his class, then you'll understand. If not, you're in the dark. As far as the calibration use.
Oh, come on!
In terms of the calibration and use of this device, the arm itself has the 72 teeth of the ratchet, and we identify the 0 point where it's fully extended. Similarly, the digital goniometer can be zeroed at any location, so we wanted to make sure those were lined up correctly before zeroing it. Once it's turned on, then just as a check, you can go up to 90 degrees, which is marked on the teeth as well, and the goniometer reads the same angle. Clicks into place and doesn't fall back down until you release the pawl, and then it can be pushed back down. It also has the extended range of motion for hyperflexion, or hyperextension, sorry. The maximum flexion of the device is 166 degrees, and the hyperextension goes to -19, which is pretty far beyond where most people can get, but it's not impossible. Our budget for the device came in well under $1,000. The structure, measurement, and transportation sections came in right around $182. This is a more detailed view of that budget. If you have any specific questions, we can come back to this. It's mainly talking about the different fasteners and the individual parts. Some future improvements would be adding ballistics gel or a similar material to simulate the soft tissue feel that's found in the arm. The skin, bone, skin and muscles and everything prevent full range of motion. And adding this would be a more realistic option. And we could also add a form-fitted ratchet covering to prevent the pawl from engaging with all the teeth. This could simulate arthritis, tennis elbow, or surgery complications. We'd like to acknowledge our project advisor, Dr. Julian Davis, our project sponsor, Dr. Mary Kay Arvin, Dr. Art Pulaski for his biomedical expertise, our academic advisors, Dr. Brandon Field and Dr. Natasha Smith, to Mr. Amos and Mr. Nelson for helping us out in the Applied Engineering Center, to Ms. Donna Moore for keeping us on track throughout our college careers, to USI Engineering Department and USI Occupational Therapy Assistant Department for the opportunity to work on this project, as well as our friends, family, and fiancés for their support through our education. If you have any questions, we'd love to hear them.
All right, questions?
I've got a question kind of related to how this device will be used as a teaching aid. So if students are supposed to learn how to use, how to take these measurements, I'm guessing maybe should they expect to see the digital goniometer and, are they going to be using it? Is that the check on whether they're right or not, or are they actually being trained to use it instead of doing it?
Actually, a little of both. The professor is going to be on the digital goniometer side as a quick check, and the student would always be measuring on the side of the line aisle. They can use their ordinary analog digital goniometer, and then potentially some testing could be done to see the efficacy of a digital goniometer in a flexible setting, to see which is more accurate.
Thanks, Nick and Brent. So how many bones did you have to run through before you finally got the ratchet and pawl attached properly?
We actually got it done with just the one set of bones. We didn't make any mistakes in the beginning. We thought we bought 4 sets just in case there was mistakes made, but we actually got it done in one try. So we have 3 sets to go ahead and continue on with future work or even make more models.
They're pretty sturdy. There is one that we broke, but super glue came in handy.
The ratchet and pawl system, how durable is it? I mean, because it's got the spring that you have to disengage to make it work. How many thousands of undergraduates will that take before it doesn't go anymore?
Hopefully one like 5 to 10. It should be fairly sturdy. The metal we used was actually from a bandsaw blade with the teeth cut off. It's fairly stringy, and if it does wear out over time, then it's easily replaceable.
The ratchet and pawl themselves are actually made of brass, so we did see a little, the metal strip was kind of gouging the pawl at first, but a little electrical tape around the tip there keeps that from happening.
You mentioned how difficult it was to set the holes.
Yes.
And, did you consider trying to scan that to create a CAD model, a solid model of the whole thing?
We did. Doing that and then trying to find a way to drill that hole afterwards, it just made more sense for us to go through the geometry and keep it leveled the way we saw that would be needed to align everything correctly. It's just the main issue was keeping the ball's hole correctly spaced from the ratchet center hole. It's just the bones are not a standard surface you're working with, so aligning that was a bit of a challenge. Now that we have it placed, though, future work could be repeated just based on that hole. It would speed up the build process considerably.
All right, any other questions? Let's give them a hand.